right. So let's start our science
yeah, no, sorry, go ahead.
meet industry session. I think it's time to go ahead. Yeah, of course, MCQST is basic science research effort, but nevertheless, we have a strong commitment, first of all, to public engagement. So we have to make public aware of what quantum science and technology is good for, but we also have a strong commitment in rapidly transferring achievements from basic science to industrial applications. And that's why we have organized this meeting now. And we have, unfortunately, not 5, but only 4 participating companies. So this is Infineon Technologies from Munich, represented by Sebastian Luber, Director of Technology and Innovation. Then IQM Germany, I just saw Enrique, CEO of IQM Germany, jumping in. And then we have Kiutra GmbH, represented by Alexander Regnat, and the Leibniz Computing Center, represented by the head of quantum computing, Luigi Iapicino. And unfortunately, Johannes Werst couldn't make it due to health problems, and so we are only 4 companies. So the program is as follows. First, we have an introduction of say 4 companies and also the people representing the companies. And after each presentation, we have a 5 minutes discussion. And then we will, at the end, go into general questions on quantum computing, quantum technology in Germany and all over the world. So, okay, I would say we start with Sebastian Luber of Infineon Technologies. Sebastian, please unmute yourself and start with your slideshow.
Thank you very much. So it's thank you that I have the opportunity to be part of such a great virtual event. It's really impressive what you set up. So within the next minutes, I'm going to explain a view from Infineon Technologies, so a view from a large semiconductor corporation on quantum technologies, and elaborate a bit whether we see it either as a threat or an opportunity, or perhaps also both. So of course, first of all, we have to motivate here in the company, why are we looking into this fascinating field of second generation quantum technologies? And then where do we see the impact on our business, on our development? And then last, I will explain shortly where are potential benefits for a collaboration between semiconductor industry and especially research. So if you look at the press, quantum computing, everybody knows here. I'm sure, especially in last year autumn, with Google pronouncing that they achieved the quantum advantage or quantum supremacy, made also the way into a daily press. So really, at every major newspaper you could read about it. But also consulting companies a few years ago also jumped on the topic and had several publications on that. So also from that side, you got the motivation within a company to look into this field. And if you're dealing with a quantum flagship initiative, then of course you know the future is quantum. So from an Infineon point of view, we are a large supplier of semiconductor technologies. And we are also one of the largest suppliers of security solutions. So as you all probably know, quantum computers have a potential impact on cryptography. So of course, we have to look into this field to know on potential attacks to make our products secure and safe. But also on the standard devices which we provide to the community, which we provide to the people, so transistors or sensors or whatever, we rely on quantum effects, which you usually say it's the first generation. But of course, we have to look at developments in the field to be sure that we don't miss a development, that we also always are able to provide the best solutions. So this is from supplier point of view, but also within our company, we have, of course, many fields where we apply computers, where we apply high performance computing. So also there, it's a potential benefit, a potential advantage to look into quantum computing. So perhaps we could get an advantage of using there the great possibilities, the vast possibilities of quantum computing to improve our products, to improve our development. So especially in supply chain and in simulation, we currently have projects ongoing where we evaluate potential benefits of quantum simulation or quantum computing. But also in other fields where you wouldn't think of so much, we could potentially benefit from quantum technologies of the second generation. So we have very specialized sensor applications, measurement applications, where we have to look deeply into what is going on the semiconductor level. And if there is a possibility to have here better equipment, to have here better measurement equipment, we would definitely have a benefit from that. So there are two sides which makes it interesting for a semiconductor corporation to look into this field. Either think about being a supplier into quantum technology or using quantum technologies for your products, but also as a user. So using advanced computation technologies such as quantum computing to be better suited in development. So perhaps a bit more details on the cryptography. So as already said, we provide security solutions, and it is already known that the public or the quantum algorithms like Shor algorithm, Grover algorithm pose a threat to typical standard cryptography methods, which we use also in our products. So we have to already now work on so-called post-quantum cryptography, which we're also doing. And why do we have to do it already now? So if you look here at a sketch where you see, let's assume the quantum computing age would start roughly in 2020, so in 10 years from now. If you think about consumer devices, which have a lifetime of roughly 5 to 8 years, then there's still time to prepare. But if you think about cars or even infrastructure equipment, it should have a lifetime of 20 to 30 years. So either you make this equipment able to upgrade during the lifetime, or you have to already implement now secure cryptography methods to be safe even when there's a general purpose quantum computer available. So that's what we are also doing. So there are several people in the company working on new cryptographic methods. For example, the so-called New Hope algorithm has been submitted to the NIST post-quantum standardization project. And also we have several funded projects ongoing where we exactly look into this topic. On the other side, we also look at sensors, so quantum sensing. A very prominent example here are the nitrogen vacancy centers in diamond. Whether we could provide here better sensors, more accurate sensors. And just to show you a typical application where we usually sell our magnetic sensors into, it's shown here, a motor application where you have a magnet and a sensor, an angle sensor, and by that you control or you detect the angle of the motor. But there are two constraints in industry which you have to always have in mind whether it's possible to use a new technology. First of all, you have tough requirements. For example, if you go to the automotive world, it's 200 degrees Celsius, which you have to survive, and lifetimes of 15 years. So really, it has to be a very reliable technology. And then, of course, it's cost. So you usually compete with another technology or many other technologies. This is very different, to my opinion, to quantum computing, where you really have a kind of a disruptive potential. In sensing, we rather see it as an evolution. So you have to always compete to current sensors such as a tunnel magnetoresistance sensor with costs or prices below €1. And here exactly, I think, is also a challenge for these new sensors. Usually to get such a new technology into the market, you need at least 30% performance increase, or if it's a completely new technology, even 100% better performance. And this for the moment, at least, or could also be for the costs. And this for the moment, I think, is still very hard to achieve. So we still need basic research in order to improve the sensors. And then we will see, will it still be dedicated to special applications or really make the way to volume applications? Then speaking in the last few minutes on where collaboration between semiconductor industry and research, I think, is necessary in order to further improve the performance of quantum computing. So if you think about the current systems where, for example, Google or IBM announce that they have more than 50 qubits working, you usually see the pictures of the cryostats with a lot of wiring, a lot of different levels of temperatures. You could think of increasing the number of qubits by a factor using the same technology. But if you want to move to real life applications like quantum chemistry or even factoring cryptography, you need much more qubits, and you can't really imagine how you will do this with this standard approach. So probably you need more other development steps in order to make this possible. And exactly here, I think semiconductor industry is very valuable, and also the approaches, the development approaches, but also production can really help here or is needed. So just one example where Infineon, for example, is looking into, also in discussion with IQM, for example, where you have control electronics for your quantum computer and lots of connectors here between the control electronics outside the diffusion fridge and your qubit layer. So of course you should think of reducing these connections and also moving the control electronics to the cryogenic temperatures. Other things are also where usually I think research is struggling or could profit a lot from a collaboration with semiconductor industry are packaging technologies. So especially here in this combining the qubit chip with control electronics or also readout electronics, you also very often see such a 3D integration. And especially here, for example, this is a picture from Infineon with MEMS industry, you're very much into this topic. But also, we also have good discussions currently with IQM and Walter Meissen Institute on the manufacturing itself. Very often you still use a lab approach for the fabrication of a qubit layer, which has, of course, their justification, but in order to scale it up, you probably have to move on to a more industrial approach in production. And especially here, again, magnetoresistive sensors have similar challenges regarding insulation and regarding deposition of such thin layers, very reliable and very reproducible. So I'm a bit running out of time, so perhaps one last slide. Another example where we already work together with research here, especially with the University of Innsbruck, is on ion trap quantum computing, and especially on the production, on using the production and development flows of Infineon. I think we made a very good step forward. So what you see here is an ion trap device of a two collinear trap device, which is fabricated in our facility in Villach, where you have a multi-layer process. So for us, it's not so difficult to produce it, but if you would do this in a research lab, probably it would give you a lot of headache. And here, recent results where it could be demonstrated by the University of Innsbruck, where you have different lattices created by this surface trap. So to conclude, what Infineon does regarding quantum technologies, we already prepare here, especially on security solutions. So we already adapt now. We actively look into the topic of quantum sensors, which to my opinion is an application which might be very close, but you always have to compete to current sensors. And then regarding especially manufacturing, integration, scaling, and also complex project management, there a collaboration between research and industry, I think, is very beneficial to move forward. Thank you very much.
Yeah, thank you, Sebastian. And I will ask John, are there questions already around?
John, you're still muted.
John, you are muted.
So there are no questions in the chat room right now, but maybe I could ask one.
Sure.
So I mean, I think it's very clear. I agree entirely with your kind of idea that close cooperation between basic research and industries kind of required. What kind of mechanisms would be good for Infineon to allow that kind of close cooperation? Because quite often there are some hurdles regarding intellectual property rights and things like that, and for, let's say, ad hoc collaborations, that can sometimes be a bit of a barrier to kind of rapid and close collaboration. So what kind of things does Infineon envisage, and what kind of projects there do you think of?
I think there are multiple possibilities. Of course, we usually try to work together in the framework of a publicly funded project, because very often if you work together with research, it's on a topic which has a high risk regarding potential business. So you need some funding in order to justify that you put resources in it. And of course, it's always an issue if there are law departments on university and on company side trying to figure out how to structure IP, intellectual property. But I think usually you always find a solution, so that's not a problem. And once this is established, then also it's usually very easy to do an ad hoc collaboration, as you name it. So whenever you have already this framework, then it's usually also very easy to put something else in or to do a processing on an existing mask set, which is anyway run it within such a project. So I think creating the network and also a network of joint projects then allows also to be very, very flexible.
Okay, may I just add? You were mentioning the challenges regarding fabrication and scaling of quantum circuits. And you were mentioning that it would be nice to have joint efforts between research and industry. Do you have an idea how this could be implemented in a reasonable and not too long timescale way?
Yeah, I think we already made first steps also with the Walter Mice Institute. So for us, of course, it's always a challenge to introduce new materials to existing production lines. But we already, for example, in Regensburg have production lines dealing with what we call critical materials, so materials which you don't have in a standard semiconductor production line. So we have a certain flexibility where we, for example, could look into superconducting materials as well and see whether we can use existing production lines to fabricate superconducting circuits. But of course, there's a certain limit. So to use more exotic materials there, I think research or RTOs facilities are needed, which have there much more flexibility to look into this. But to have here a close link that also the expertise from industry on large volume production or high reproducible production is transferred to research, I think this would help then to speed up later the transfer from research labs into industry.
So maybe we do have a question that's been posted into the question portal, and that is, could you go into some details about the manufacturing process for quantum circuits or circuits related to quantum technologies?
I don't have a slide prepared for that, but I think it's perhaps perhaps to look into this where you see a cross section of a magnetoresistive sensor. So usually you have below the silicon devices, which I think in most of the quantum technologies are usually, it's not fully true, but at least in superconducting circuits and also in diamonds, you don't use a silicon layer beneath, but everything happens here in this so-called back end of line. So the metallization, and of course you need their special production facilities and also equipment which is suitable, for example in this case, to deposit on a nanometer scale or even angstrom scale uniform layers, and then also do an oxidation. So this is, for example, which you could also use in order to do a Josephson junction. Quality we still have to look at, but these are very specialized equipment which is suitable for this excellent uniformity.
Okay, John, do you have more questions or could we go on?
I think we could go on right now and maybe come back if we have some other questions later on. So maybe people can ask questions to any of our industry representatives at any time, and we can come back in the general discussion.
Sure, yeah.
Okay.
Thank you then.
So thanks again, Sebastian. And then we go on with Enrique Solano, CEO of IQM. First of all, Enrique, welcome back to Munich, not in science, but now in business. So we are looking forward what you are telling us about IQM. And I also would like to ask the speakers just to introduce themselves a little bit. I will not do that.
Okay, now you see my screen, right?
Yes, wonderful.
Okay, so, I mean, to introduce me, it's not easy, but let's say that I, just to summarize the last few years, I have been for 7 years in Munich, arriving to work in Max Planck Institute for Quantum Optics with Professor Walter, so I was doing the theory of microwave cavity QED for quantum optics, then 3 years in theory with Ignacio Cirac. Then I started to work independently on superconducting circuits when the wave of Yale arrived in 2004. Then all the quantum opticians were telling me that that was nonsense, that there is nothing new, that all these systems are dirty. And suddenly I trusted and I started to work, and then we approached to Rudolf and Walter Mainzer Institute, and we started to do wonderful things together in theory and experiments. Then I was moved to LMU because of this condensed matter influence. Then I was called back to Bilbao. I have been director of a quantum computing center there for 12 years. And also in the last 2-3 years, I've been director of a quantum artificial intelligence center in Shanghai, China. And since March this year, I'm CEO of IQM Germany, this company that is leading in fabricating quantum computers in Europe. So that's more or less a short summary. I'm very proud that Rudolf is hosting this, also Jonathan Finley and all the friends in Munich, that we will meet us personally soon. The company IQM Germany is a subsidiary of IQM Finland and has been created with a clear goal to lead in Germany the entrepreneurial efforts in quantum computers with superconducting circuits. But if you follow a little bit my career, if I remember when I was young, I was telling my students, tell me which are the 4 most important and influential research groups in the world. And they mentioned this, that, and that. And I replied to them, okay, all that physics is not interesting for us by definition. Otherwise, you cannot do original stuff. And here in IQM Germany, we are boosting the same approach, where we are saying, how can we contribute to quantum computing with superconducting circuits in a totally originally European-based ideas? And this is the concept that we are calling now co-design quantum computers that I will share with you in few slides. Huh? I will try to make it in 10 minutes, but I guess if I make it in 12, it is fine. So literally, professor style, I will make some definitions. So co-design quantum computers is just a quantum processor where we abandon all prejudices and all trends and all universalities and all mathematics and all influence of classical computers, and we ask ourselves which is the available hardware and the possibilities of the hardware, and which is the model we need to map for computing. And we try to adapt the hardware to the software and the software to the hardware in such a way that the matching is, if not optimal, close to optimal. I will explain you this a little more, but it is a matching of hardware and software for specific purpose that typically the purpose is provided by the clients. So we will tend to avoid solving academic problems that are interesting, and we will start constantly by the customer needs, and we will deconstruct them back towards the hardware and the software in a way of shortcutting the quantum volume and advancing towards quantum advantage. That for us is not the same as quantum supremacy. Quantum supremacy is outperforming classical computers, and quantum advantage is doing it for a acclaimed, let's say, useful goal. In my second line, you can see another original statement that is, of course, open to discussion and not agreed by many, that when people call NISQ architecture, most people think that it is just these boring square cells, nearest neighbor, connected qubits that are noisy, and that we are going to make 1 and 2 qubit gates. We think that the matching between those NISQ architectures and digital quantum algorithms, that is the current trends, is arguably the worst matching between hardware and software. And we have been developing many, many papers, and there are already several experiments proving that statement in a trivial manner, which is, if you think it 1 minute, I mean, this is very easy to follow. And among these co-design quantum computers, we have like 3 main research lines. Digital analog quantum computing is one of them, where we merge the digital and the analog paradigms. There are a lot of papers, theory and experiments, and new ones coming, and algorithms and applications, but it is just the tip of the iceberg, because we are also advancing what we call digital adiabatic quantum computing, which is even improve the coherent quantum annihilers, so the second improvement onto D-wave in coherent architectures. And there is also neuromorphic quantum computing, that is the most efficient way of mimicking memory-based, non-Markovian, machine learning, non-linear models that are the most interesting. And our goal as a company is not to live 1 single day in the quantum winter. So that's at least my personal challenge, and that's a challenge we have in our company. So just that you get briefly the point, what is digital analog quantum computing? I just have put there a few plots and diagrams. We are using digital steps that are just 1 qubit gates mostly, but it could be also 2 qubit gates. And we try to combine them with something that we call analog blocks. Analog blocks are inspired in analog quantum simulators that are just many qubits or many devices always on or connected by multiple couplings. And there are 2 kinds of analog blocks in the way we have developed the field in the last 10 years. One of them is just turning on like multi-qubit gates, but not for fixed interaction times, but for an arbitrary interaction time. So in the same spirit of analog quantum simulators. but also we call analog block when, for example, in a certain model, the vibrational degrees of freedom of a molecule for drug design uses harmonic oscillators. We never understood why the harmonic oscillators in quantum computing are reduced to qubits, because in superconducting circuits, we have robust long coherence times and controllable harmonic oscillators. And the best example that we have for that, we have several papers also, is when people do, for example, applications of quantum computing to physical models or financial models that require a continuum of bosonic modes. And the continuum of bosonic modes, people go like the experts in high energy physics, discretize the continuum. They have thousands and millions of discrete harmonic oscillators, and each of these harmonic oscillators with many populated excitations, they are turned into qubits. At the end, you end up in the same. You need millions and millions of qubits to map such a simple thing. In superconducting circuits, you have an open transmission line that if you are clever enough, you can tune it correctly such that a continuum of bosonic modes is represented by a continuum of bosonic modes, which makes the approach towards quantum supremacy an advantage much, much simpler and efficient. You see? And then we have two versions of the digital analog quantum simulator or computer. We call it stepwise or the banked approach, because the stepwise is more pedagogical. You say an analog block, a digital step, and so on. But you can also keep on continuously the analog block, and just to click that analog block with digital operations. And we have proved that such a device for current possibilities of the architectures are even universal. That means that you could do absolutely everything, only that you pay the price that you cannot do error correction, but nobody wants to make error correction. And also the price that, of course, the creativity that you need for algorithms is much higher. It's less deductive, it's more inductive. Inductive is the nicest part of arts and engineering. The deductive creativity is the most boring one, at least for me. So the other example I have here is a paper that we did with Frank Wilhelm and Mercedes-Benz and my team in Bilbao, Spain. And we showed how if you use the stepwise digital analog quantum computing or the banked digital analog quantum computing for the QAOA algorithm, we can do it better by a factor of 3 to 10 in the number of operations and in the coherence time. And this was cool and submitted to publication. So we will see how to publish somewhere. And for us, the most important experimental result confirming our, let's say, concepts is this independent work of Alexandre Blais and Andreas Wallraff in ETH Zurich, where they have done also the QAOA algorithm, but they have used, instead of fixed 2-qubit gates, they have allowed that the interaction time of the 2-qubit gates are continuous. So this is the first example in the lab of a digital analog quantum computing paradigm, as Andreas agreed, at least, that can show that he gained a factor of 3 in comparison with in interaction time, in comparison in the number of steps, in comparison with the conventional digital methods. So this is also a proof that the ideas of maximizing the mapping of the model of the software to the hardware and not accepting the simple rules of digital quantum computing is a nice way to go. Just now more on the business level, for IQM Germany, we have designed this, what we call co-design level 1, level 2, level 3. The level 1 is kind of a proof of concept, and this is what I have been doing in the last 10 years. And we will be doing this still in the company, because if some customers, like they're approaching now by dozens, right? We are being very successful in the approach of customers. And they say, okay, I don't believe you that this works better. Then what we are doing is offering for their use cases to develop digital analog quantum algorithms and to run them in the standard NISQ architectures and to prove that we can do better. And this we are doing systematically. It's not very hard to do that, really. In 3 to 6 months, we can deliver such proof of concept very easily. The level 2 of co-design is more advanced, because if the customer or the people that request the service or are interested in our ideas, we we can go to co-design level 2, where we don't have to prove that such a co-design approach is better. And we are going now to improve and to adapt the hardware to the digital analog quantum algorithm. That means that in the co-design level 1, the architecture was not optimized for such a concept, and it was better. So now we improve on switching on and off analog blocks. We make studies of the spurious resonances, of the massive couplings. We make a real professional engineering architecture. And then we expect a strong improvement. So many quantum algorithms will approach the supremacy or the advantage level. And the co-design level 3, that is the one that I like the most, is the most inductive in terms of creativity, is that we start by customers come and said, look, Black-Scholes equations for financial models, turbulent regime of the Navier-Stokes equations for fluid dynamics, logistic network optimization for traffic flow or for airplanes or for networks in a telecom company. Then what we do is we start by the use cases and we decompose them or deconstruct them into an optimized hardware and software, such that we promise and we offer the possibility of reaching usefulness, that means quantum advantage, with a few hundreds of quantum devices, big qubits, big cavities, or the like. And that's more or less the challenge. And the level 2 and level 3 imply the construction of the hardware. So the level of investment that is needed is there. And as you can imagine, level 2 and level 3 will not be funded or paid by customers if they are not bottleneck or billion-dollar problems in the industry, right? So level 1 can be academic, can be proof of concept, but level 2 and level 3 request higher levels of investments, and therefore the problems to tackle has to be use cases. And the advantages, just to finish, are of course that we develop IQM quantum software and IQM quantum hardware hand in hand as a unique concept. From that point of view, we try to develop a product that is identified with our company, not following American standards or Asiatic standards, but a more European concept in terms of IP, property, development, hardware ecosystem, and so on. Also, we create new companies and new startups because we need new middleware, we need new optimizers of quantum algorithms. The advantage too is that we can compete worldwide because we have a faster approach to advantage for academic and industrial use cases. And the 3, of course, we should never forget that there is a geopolitics issue in this. And our opinion and strategy is that we have to be different. Otherwise, by doing the same, with the same ideas, with the same software and with the same hardware, what others are doing with budgets that are 100 times higher, I think this is a lost cause. So we try to compete at the highest level, but with originality and products that can be reached faster. And this is the end, just the more or less like you can see it as a global business plan. There is no difference between hardware and software for us. We are a company that builds hardware and builds software all together. We will never disregard the quantum computers done for education and for research, because we think that there is a huge potential market, even an education in the schools, universities, and also below at the recreational level of mobile apps, gaming, and recreation, also for proof of concept algorithms, and the outreach concerning quantum computers in exhibition, control, that the public and the society see this evolving. And the central line is the co-design level 1, level 2, level 3 that we develop for collaborators, more research-like partners to accompany them in their development, and clients that want to buy quantum computers. So that's the end of my talk. Thanks a lot.
Yeah, thanks, Enrique. John, did you receive questions?
So far, no questions from the audience, but I had one, Enrique. So thanks very much for your nice talk. You mentioned as part of your presentation that there is a bit of a different culture within Europe and say the United States when it comes to things like IP, intellectual property rights and things like this. But there's also a kind of different culture with regards to, let's say, entrepreneurship and to what extent people are willing to invest in real blue sky ideas. Could you comment on where those differences are and how we can kind of get around them?
Very, very nice question, John. Exactly, that's obvious, right? This is historic, the entrepreneurial mentality of the society in US, for example, in Canada also, and very recently in China. So I have the luck to have been working in the 3 continents, let's say, and I know pretty well the mentality, and China is also boosting strongly this entrepreneurial aspect. I would say that in Europe, what we are trying to do at IQM is, of course, to lead, to be considered as a European company, private company, boosting hardware and software in quantum computing. But it is not that we are happy to be alone or almost alone. It is, in fact, sad. We need more initiatives at the hardware level. That's the way. Even though you know that I am a theorist from education, I really miss that, and I tell you why. Because we think in the field and in the countries and the investments, and I suffer. That's why I jumped from the academia to the company, right? Literally, one of the reasons is that I realized that the quantity of software companies around is so huge. And when you tell them where will your algorithms run efficiently for usefulness, the answer is others will build the beautiful quantum computer, right? So always, I do the nice thing, but others will build the quantum. And that's something that, at least in Europe, should be stopped, not the growth of software companies, but let's say the motivation to the younger people to go towards hardware in trapped ions, in optical lattices, in quantum dots. We need hardware. Otherwise, you see, probably you remember these criticisms of Asher Perez, when he said quantum phenomena happen in the lab, not in the Hilbert space, right? So all these software companies are running in the Hilbert space because there is no quantum computer that will profit from such algorithms now, right? And that's the way I see Europe, but it's not only Europe. You see that in US also are less companies of hardware, but in Europe we have to promote more hardware approaches. Ours is mixed, but to promote hardware in Europe would be fantastic.
Okay, Enrique, you are already addressing an important topic we probably have to discuss also later on. But you were presenting a very nice strategy. So of course the question always is, what do you think are the bottlenecks showing up? Is this money, people, hardware, or are there roadblockers you have to remove? What is your opinion about that?
Yeah, my opinion is very optimistic. So let's say people always try to put me the label that I am against digital error-corrected quantum computers. I think this has to be boosted. What I don't want is to find myself and ourselves in 2-3 years when people saying, everybody laughing at us, saying, you see, you failed. You see, the quantum winter now takes 30 years. That's not, and the bottlenecks for me, literally in this moment, are the incapacity of our community to abandon the comfort zone of a general theory of quantum computer that is not matching the hardware possibilities. You see, and of course people say, yeah, but then you are a pessimistic. No, there are alternatives. You can, for example, we created the combination of digital with analog. It's absurd, right? Analog has very well-defined problems. Digital is universal, but the overhead is huge. I mean, just combine them, merge them. And people say, okay, this looks like a kitchen, right? You are mixing rice with salt. But I think that this kitchen may take 20, 30 years. And I think we have to continue with our, and that's what we are trying to do. And the bottleneck is, I think, the mindset that there is still creativity in software and in hardware that has to be boosted by younger companies. And I trust in the younger generations for doing it.
Okay. So we are already a little bit over time. So I think
we would have one question in the. So the question from a member of the attendees is, where do you see opportunities to work with other quantum computing hardware providers and platforms?
Good point. Essentially, of course, I cannot disclose names, but the persons that are asking themselves such questions should know that we are, and our emails and our telephones are being attacked by the top software companies in the world in the last weeks and months, because they see a path to develop novel software, right? For example, for digital analog, you don't have good transpilers, compilers. I don't mention the names, but if you put in your head the name of the 5 most well-known software companies, they are lobbying with us for building this. And also inside Europe, top software companies are going to do that with us. And that's great, because then our ecosystem in Germany, for example, will also create software companies, but that are creating software for a different kind of hardware. And this gives us also some what people call sovereignty, right? I don't like much the word, sounds a little word-like, but gives us independence, let's say, technological independence. And that's the way we're doing. So yes, we are different, and this looks like isolation, but we are very glad to share with you that hardware and software companies are developing partnership with us that will be announced soon.
Okay, John, I think we should go on for the moment. Enrique, thank you very much again. And the next presentation is by Kiutra GmbH, and the company is represented by Alexander Regnat. So unmute yourself and share your slides with us.
Okay. Can you hear me? Great. Yes. So hello everyone from my side and Kiutra. It's a great pleasure, of course, to be here today and join this year's MTQST conference in this virtual, very innovative and virtual new way. And I would first like to thank the organizers for making this possible despite this unprecedented situation caused by the COVID-19 pandemic. My name is Alexander Regnat. I'm the CEO and one of the co-founders of Kiutra. And just to briefly introduce myself, as Professor Gross asked, I also studied here in Munich. I'm an alumnus of the Technical University of Munich, the Department of Physics, where I did my studies and also did my PhD thesis in the group of Professor Christian Pfleiderer at the Chair for Topology of Correlated Systems. And as you will see, that's why we also built Kiutra, because we developed a new cooling platform or new cooling device, which is very useful, as you might see, also for this growing field of quantum science and technology. So our mission at Kiutra is to provide cryogenics for quantum science and technology, where our focus is on easy-to-use cryostats to support the fundamental science and material science, on rapid prototyping tools, which help to accelerate the development and increase the productivity, for instance, in the testing and pre-characterization of quantum hardware. And finally, we focus on cooling platforms that provide continuous sub-Kelvin cooling, but at the same time, helium-3 free cooling. And this is because we believe that such helium-3 free cooling will be key for future scalable applications of quantum electronics. So Kiutra is part of the scientific community. We are doing our own R&D to constantly improve our magnetic cooling technology and to come up with innovative, truly cryogen-free cooling solutions. This mindset is also reflected in several corporate memberships, like for instance, in the International Society for Sample Environment. And it certainly originates from our roots. As I already mentioned in the beginning, Kiutra was incorporated in 2018 as a spin-off company from the Technical University of Munich, the Department of Physics. And just in 2019, we set up our own office and production in Munich, Obersendling. So Kiutra has a small but very agile and of course a very competent expert team with several low temperature physicists who bring in many years of hands-on experience in cryoengineering and of course magnetic refrigeration. And our team is also constantly growing. So if you are interested in joining Kiutra, please have a look also on our website or send an email to talents@kiutra.com. Now, before showing you our products, I would first like to briefly at least introduce you to our cooling technology, and that is magnetic refrigeration. Magnetic refrigeration, also known as ADR, which is short for adiabatic demagnetization refrigeration, is a very well-established technique to provide sub-Kelvin cooling, typically for several hours, so limited in time. And this method does not require helium-3. It can actually be implemented completely cryogen-free, which makes it a very simple to use and robust tool. So the working principle of the ADR is based on the magnetocaloric effect of a solid state cooling medium. It is shown in this infographic here, but I will only summarize the most important points. So in the first step of the ADR principle, the cooling medium is magnetized, and the heat of magnetization is dissipated in a heat bath, for instance, a mechanical cryocooler. The refrigerant is then disconnected, shown in panel 4 here, from its surroundings, particularly from that heat bath, and then demagnetized adiabatically. And due to the magnetocaloric effect, the temperature of the cooling medium now drops as the field is lowered. So this can now be used to cool a sample, which is attached to that cooling medium, typically for several hours. And once the field has been reduced to 0, the overall process can be repeated by remagnetizing, by regenerating the cooling medium. So the ADR principle is realized, for instance, in our L100F cryostat. So this cryostat contains a single ADR unit, as it is sketched here on the right side of this photograph. And therefore it offers single shot. This is temporary cooling with hold times in the sub-Kelvin regime of typically several hours. So like here, slightly more than 20 hours at 500 millikelvin. Now, this limitation in the cooling time can be overcome by not just using a single ADR unit, but actually using multiple ADR units. Such multi-stage ADR allow to regenerate one ADR unit while the cooling is done by another ADR unit. And in fact, Kiutra is the first supplier for such multi-stage ADR systems, which now offer cryogen-free, particularly helium-3 free cooling in the sub-Kelvin range, and at the same time, permanent sub-Kelvin cooling. So this CADR principle is implemented, for instance, in our L302C cryostat. So this cryostat now contains 3 ADR units, as it's sketched here on the right side of the slide, in a serial configuration. And it again offers, of course, single shot, standard, temporary ADR operation down to 80 millikelvin, but it now also offers additionally continuous CADR operation down to 500 millikelvin. At least we specified to 500 millikelvin. As you can see in this graph, it even works at lower temperatures like here, 300 millikelvin in continuous operation. So based on this ADR and CADR principle, Kiutra builds cooling solutions that stand out due to, of course, their cryogen-free operation independent of helium-3, which makes them affordable and future-proof, a very large temperature range that can be accessed with these cryostats, making these systems very cost-effective. They are fully automatic and robust operation, making these systems also very fast and reliable, and in fact an ideal tool if you consider rapid prototyping, screening of large amounts of samples, or R&D in shared facilities. Finally, our cryostats offer a very modular architecture and upgradability, making these systems very versatile and highly configurable. So Kiutra cryostats are currently offered in two form factors shown here, namely the smaller S-type on the left-hand side and the slightly larger L-type on the right-hand side. Both cryostats can be extended with several add-ons, and most importantly, they can be configured according to user cooling requirements with either up to 2 or even up to 4 ADR units for the S and L type respectively. The S-type cryostat was designed for the development and operation of quantum devices like photon sources and detectors, and it features a wide temperature range in a very compact housing that can even be integrated into a standard 19-inch rack. So this system, of course, runs fully automatically and can be configured with 0, 1, or 2 ADR units for cryocooler only operation, ADR, so standard single-shot ADR operation, or CADR continuous operation, respectively. For some configurations, we also offer optical access. The slightly larger L-type cryostat is optimized for the simple and fast characterization and the prototyping of quantum matter and quantum electronics. And it offers, again, cryogen-free operation, a large temperature range, and of course, stray field compensated ADR magnets, if required, also with magnetic additional mu metal shielding. And of course, again, the system runs fully automatically and can now be configured with 0, 1, 2, 3, or even 4 ADR units for cryocooler only operation, single shot standard ADR operation, or various modes of continuous CADR operation. And the L-type cryostat can further be extended, for instance, with our automatic sample changer, making it an ideal tool for the fast screening of material samples and quantum hardware. So our sample changer is shown in the slide. It's a fully automatic top loading load lock system, and it actually allows to load or unload samples in about 5 minutes only. So the sample is mounted on a puck, which is then loaded into the cryostat. And once loaded into the cryostat, the sample is cooled to below 4 Kelvin in typically less than an hour, which is much faster than cooling is done with standard helium-3 based cooling systems. Once cooled to 4 Kelvin, we can go further down in temperature, and cooling to the sub-Kelvin temperature regime altogether takes approximately 2 to 3 hours, depending, of course, on the heat load and the ADR configuration of that cryostat. So if you would like to learn more about that sample changer or even see it in action, please also have a look at our poster, where we have added as an annotation a short video clip that demonstrates this sample loading process. Okay, so finally here some concluding remarks. Perhaps as the bottom line, we here at Kiutra, we offer cryogen-free cooling solutions and accessories for QST. We have relatively short delivery times of typically 8 months for standard systems. And it's worth to mention also that we have special offers tailored to needs of early career scientists, starting already at 220,000 euro, which is very affordable compared to other existing solutions. Of course, if you would like to learn more about our company and products, please get in contact. You can meet us here at the MCQST conference at our virtual booth. You can just visit us at our head office in Munich, or visit us online, of course, and schedule a call or demo. I think that's it. Thank you very much for listening. If there should be any questions now, I will be very happy to answer them now or later during our discussion.
Yeah, thanks a lot, Alexander. So I will have a look to John. Did you receive questions?
So we did, yeah. So one of the questions is, does the ADR technique result in heat dissipation to the ambient, so the ambient environment?
Yes, so of course we dissipate ADR energy that originates from the ADR, and it's dissipated in the pre-cooling unit, so the heat bath, which in the standard implementation that we use is a mechanical cryocooler. So usually a pulse tube cryocooler, and that cryocooler dumps energy to the atmosphere. Yes. So that is usually operated using a compressor, and that's where the energy is dumped. The energy of the ADR unit itself is very small.
I think it was on some of your plots, but the cooling power that you can develop.
Yeah, so that's the cooling power for the CADR operation is depending, of course, on the configuration in the range of several 10 or 100 microwatt. Depending also, of course, on the operating temperature. And that is, of course, smaller compared to dilution refrigerators. So that's probably one of the major drawbacks of the ADR and CADR cooling technique. But at least now we can already offer a true cooling power, which hasn't been around for many years. So in the standard implementation, there was no cooling power at all. There was just a cooling capacity. Now, for the first time, we can already provide true continuous cooling and a cooling power, and we're working to increase that cooling power to also make other applications feasible with this type of ADR and CADR cryostats.
Okay. Another question which has just come in is, can you tell us something about the mechanical vibration levels at the sample stage?
Yeah, so they are completely due to the mechanical cryocooler, and it actually depends which on the cryocooler you're using. So we usually recommend to use Sumitomo or Cryomag pulse tube systems with remote rotary valve, and then you end up with typical vibrations you have in any similar system of some micrometers. For the L-type cryostat. This can further be reduced with vibration isolation systems. That's something we're working on now. For the larger systems, that's also the reason why right now we're only offering fiber access and no free beam access. For the smaller system, there's already the option to have free beam access.
Okay, so that was all the questions that were in the portal.
Yeah, I love to hear that you have this very rapid sample changing. Of course, people working on superconducting qubits are asking us then, is this still possible when you have wiring with a lot of microwave lines and something like that? I think then probably this key advantage is lost.
We can offer RF wiring, but of course not several hundred lines, but that's not due to the sample changing process. It's rather, so this limitation rather originates from the limited cooling power of the ADR. But we can offer the rapid sample exchange with few RF lines, which is sometimes already sufficient for the rapid screening and pre-characterization of quantum systems. And we're already working on a slightly larger pack for some hardware manufacturers, also in the US, to add additional coax connectors, allowing to do further measurements also with higher numbers of RF lines.
Okay. That's a high price for helium-3 is pushing your business, I guess. So at the moment we are paying, let's say, $5,000 per liter, and this is a key advantage of your company at the moment.
Yes, certainly. So the high helium price is an issue. Also, the availability of helium-3 in the future is at least questionable, as there aren't so many suppliers around. But helium-3 is not only expensive, it's really making the helium-3 based cooling machines rather complex in their operation. What we can offer here now, due to the lack of any cryogens, not only helium-3, but also liquid nitrogen, liquid helium-4, is that we can build highly automized, very easy to use cryostats that can also be used in shared facilities, for instance.
Okay, so thank you very much again, Alexander. And probably there are some more questions coming up at the end of the presentations. So we go on now to the next speaker. Luigi Iapacino is representing Leibniz Supercomputing Center. I'm happy to have you here, our partner institute here at Munich. So Leibniz Supercomputing Center is also an institute of the Bavarian Academy, as Walter Meissner. I am happy to allow you to start your presentation. Go ahead.
Thank you. Thanks.
Okay.
Yes, good afternoon. Start sharing my screen and let's see. Fine. So, good afternoon, everyone. For the last talk of this session, we move slightly. So far, we had industrial companies. The Leibniz Supercomputing Center is a HPC center, well, providing many more services, but in this context as an HPC center. And I want to convince you that indeed we fit into this session, and we can show, because by the very fact that we can provide services to enable innovation also in the industrial framework. So, as I was asked, just a few words about me. So, I'm an application specialist in the fields of quantum computing and astrophysics. I work in HPC at the Leibniz Supercomputing Center. What is more relevant for today, so I'm the team lead of quantum computing at LRZ, and I am the co-founder of the Bavarian Quantum Computing Exchange, the BQCX. Our poster and the industrialization is on BQCX, so you can visit it, and I will also discuss a bit about that. Okay, so after the nice introduction of Rudolf Gross, what is LRZ? So as he said, we are part of the Bavarian Academy of Sciences and Humanities. We provide services at several levels. So we provide services to the Munich universities in an equidistant way, because we are part of a different institution. We are not part of neither of the Munich universities. We provide services also to all Bavarian universities and at national level through the Gauss Center for Supercomputing and even HPC time through praise to other European institutions. Just to provide you an overview on the different levels to whom we have services available. So in Bavaria, we give HPC services and a scientific environment, the research environment, well, you know, it's very active and vibrant with Max Planck Institute for Fraunhofer Society, state institutions, and we can give access to HPC resources to these institutions in the German framework, together with the supercomputing centers in Stuttgart, in Jülich. We are part of the Gauss Center for Supercomputing. And GCS represents Germany in Europe in praise in the Partnership for Advanced Computing in Europe. In HPC, our high-end system, so our flagship system is SuperMUC NG, which at the moment is number 13 in the world. So it's non-accelerated system, consists of 6,000 nodes Intel Xeon Skylake. This is designed for high usability, since we have a huge community of academic users from many different fields of research. Therefore, a system with high usability was critical to us. And our approach to quantum computing is similar to approaches in other fields which are emerging right now. So in this slide, for example, you can see that besides HPC, there are emerging areas like AI, machine learning, big data, and all these different fields are emerging also, and they are approaching a point where they can make use of HPC facilities from a different viewpoint, of course. Traditional HPC is about modeling and simulations and trying to describe by means of equations and algorithms what are the observations of the physical reality around us, and then they provide as output data for analysis. In AI, in machine learning, we know the approach is basically opposite. So we want to learn from data, and we need computing for recognizing patterns into data, for example. And with the huge amount of data which are available nowadays from many physical different sources by large big science projects, for example, of these years, it's critical, it's crucial to integrate these new patterns into HPC. And this can be done through a circle, which is part of innovation and integration. So we want to make AI, machine learning, big data scalable. We want to use HPC systems to work on this way. And in this integration cycle and growing, and in our view also important element is given by quantum computing. Basically, we would like to insert quantum computing into the same cycle together with HPC. Integration of HPC and quantum, it's something that we are currently thinking about and working on. And from this, I can come to the approach of the Leibniz Supercomputing Center to quantum. So we see ourselves into these in different roles. First of all, we see our role of service provider and as a facility where users come to us. We want to manage the access to systems, systems that might be even not located in our center on premise, can be also remote system. This is something really relevant for quantum computing at the moment. We want to support research through consulting and also support the training and education component into the academia. We have a second role, which is the typical one of a supercomputing center. Namely, quite obviously, we host the systems. So it's something that, of course, at some point we want to think about also in quantum computing. And in hosting and operating the system, of course, as I said, one important component is given by the HPC quantum integration research. And another component which goes hand in hand with education and training, also investigate which directions are important also for training technologists in the field of HPC QC integration. A third role, which is quite crucial for us, so we have facilities, so we are a supercomputing center, but another big asset that we have users. So we have a vibrant, growing community around us, and especially in the field of quantum, we are trying to make some community building in this field. For this reason, we founded the Bavarian Quantum Computing Exchange. So we try to create awareness in this field. We try to evaluate what are the technological highlights that we can show to this community. We want to understand who is the community by means of working groups, by means of surveys, and we want to see which kind of support to the networking we can provide in this field. As already said, so the BQ6, the Bavarian Quantum Computing Exchange, is an initiative which was funded last July at the Leibniz Supercomputing Center. So the picture here is from our meeting last January, when we had still in presence meeting. During that meeting, we could welcome young girls from IQM, who is today represented by Enrique Solano. Our last in presence meeting was in March, and we started again in May with virtual meetings. Our next virtual meeting will be on August 12th. There will be a talk by Honeywell, and there will be also a series of Leibniz talks from junior members of the community, like students or younger participants to our meeting. We have meetings every second Wednesday of every month. This month we are skipping because today I'm here, so we didn't want to overlap with this conference. So we will meet next time on August the 12th. During the time, we had the representatives from IQM, as I mentioned, from Google, from Rigetti. There were from the Munich universities, of course, from the Bundeswehr. Professor Gross was our speaker as well. So we try to represent the community, the local community, but not only the local community, trying to taking advantage of this situation also for having remote speakers and try to make a service for the Bavarian community. There is a mailing list for announcements that you can join. There is a website which is slowly coming online, where you can also get resources. Then, besides the BQ6, we have also current activities. As I said, we have a user base and we have an HPC system. So for the users, we have right now the BQ6. The next component is which use we can do right now in quantum using an HPC system. For this reason, we started a collaboration with Intel. Intel is developing Intel QS, so their quantum simulator, a simulator of quantum circuits on HPC systems. It's very important to run these tools on HPC systems, because only in this case you can run quantum systems with a large number of qubits. On the right-hand side of this slide, for example, you can see some weak scaling of Intel QS done up to 1/3 of SuperMUC NG. I don't go into the detail, but if you see that several lines are overlapping well, this means that the weak scaling of the code is very good. So the code scales very well on our large system and can simulate up to 42 qubits on our system. We have, as I said, an ongoing collaboration with Intel to optimize this code on our system and on upcoming system. We have a series of tutorials and dissemination activities planned also at LRZ as soon as the situation will allow. We'll have courses and tutorials on this tool. Another activities is given by the Phase 6 implementation phase work package 8 project Quantex, which we are working on together with the IRIS Center for High-End Computing with the iCheck. In this project, we try to evaluate another category of simulators for quantum system, which is the tensor network contraction simulators. So we want to have a study of the performance of these tools. We want to develop tools and libraries that can be used efficiently on current and upcoming HPC architectures. And we want to enable the researchers to integrate the products which will be the object of this project into their own software project. And as I said, we have as target current European pre-exascale and exascale machines. This project is running already since last January, and we are in these days releasing to our stakeholders, so to the researchers supporting the project, the first software products, and we aim to have something for the community by the end of the project, which is in 1.5 years. Okay, so with this, I'm almost at the end of my presentation. As I said, I try to convince you that as a computing center, on the one hand, we try to support the innovation of our users, but also to create innovation from them. It's always our twofold role to go after the needs of the user and try to anticipate them. And we try also in this field to be successful as in other fields of our experience. Thank you very much.
Yeah, thank you, Luigi, for the presentation. Yeah, I hope that in your future we will have data on a real quantum computer and not only on simulations of a quantum computer. That would be great.
Yeah.
And I ask John now whether we have questions on your talk.
There are no questions in the portal right now.
All right. So before we are going on to the general discussion, I would just like to mention that Johannes Wurst, of course, I already said that he could not come, but the Quantum Business Network has a poster on the poster area. So you have to go there to industries, and there is a poster, and you can go there and hopefully also to chat with the company representatives. Okay. So then, of course, we can enter now the general discussion, and we were collecting a few general questions, and of course, we are also asking the audience to ask questions on what they would like to know from companies. So, John, would you like to go on?
Yeah. So there is already a question just come in from one of the members of the audience. It's directed at IQM. The question is, you use a combined hardware-software concept which uses analog and digital computing concepts. Can you tell us how this is reflected in the software architecture as compared to, say, other concepts?
On the software architecture.
Yeah.
Yeah, essentially, so let's say in this co-design level 1, for example, you take a standard square cell nearest neighbor coupled qubits that are noisy, let's say, the standard one that you can see more or less wherever. And instead of just making quantum algorithms with 1 and 2 qubit gates, we use single qubit gates and multi-qubit gates that are having the interaction time as a running parameter. So from that point of view, the quantum software is different. And when you think in controlling, so let's say more the control and the drivings and the pulses and so on, all this control just is not available, at least not at the commercial level like it's done for standard universal quantum computers. And also, even at the level of the quantum algorithms, if you go to Qiskit, Cirq, Forest, and others, of course, you could try to develop that, but this is still unavailable. And we are working on that such that when people tell us that they are interested in one of our digital analog quantum algorithms, we can optimize them given a certain hardware for their needs. But we can also change the architecture of the hardware. And then again, another variable enters there, and the matching between the hardware and the software can approach to optimize. That's the whole, and of course you have to think in the full stack and so on. So our ecosystem requires new tools. And that's why we are also trying to partner with software companies for developing, for outsourcing these new tools.
Okay, thanks very much. There was also a question for Kiutra. So for Alex, can you apply your techniques to cool down superconducting circuits? Does the magnet induce vortices in the sample, and can you cool to 15 millikelvin?
Yeah. So thanks for the question. You certainly can do this. So as I mentioned in the talk, we already use stray field compensated ADR magnets to have a minimum residual field at the sample position where you would carry out your measurement. And this can further be reduced by at least 2 orders of magnitude by adding mu metal shielding, if that's required for testing of such qubit, superconducting qubit systems. We cannot go down to, the question was 15 millikelvin?
15, yeah, 15 millikelvin.
Yeah, so that's something we cannot achieve right now. So of course we're working to go to lower temperatures. We have a limitation here because we have very modular systems. So we use smaller magnetic fields and smaller ADR cooling mediums, which allows us to build multi-stage ADR systems, so CADR systems. And you need to understand that these systems are carefully balanced. So you cannot increase the size of the magnets and the ADR media to just go to lower temperatures, but you have to improve the whole core technology. So build better heat switches and use different cooling media. So we're working on that to go to lower temperatures, and this will hopefully be soon available. But of course, at slightly higher temperatures, you can already make such measurements with superconducting systems.
Okay, thanks very much. So we have also another question, a second one for IQM. And the question is there like a virtual lab or simulating program for hardware practice of quantum computers? So do you guys have some kind of virtual platform by which people can get to grips with these digital analog systems?
Good point. We are working on that. And as I said, we had a plan to do that, and we have the plan to do that. But at this moment, we are starting negotiations because there are several software companies that would like to make this for us. And of course, to adapt them to the different platforms around the world. That's what we are doing.
Mm-hmm.
Yeah, probably we also could leave a little bit the level of details and go to the general picture we have in Germany and in Europe. Of course, you have seen in Munich, we already have many pieces. We have hardware companies, we have semiconductor industry, we have now a quantum company, and we have excellent research labs and institutions. And for me, always important question is, why don't we put all these pieces together and generate the ecosystem to compete internationally in a better way? So what is your opinion on that? What really has to be done to generate the ecosystem to make the difference? And also in comparison to the situation we have in US and China, for example. This is probably more a question to Sebastian and Enrique. Infineon is an international company, and of course you have to see your business on an international level. So in Germany, I think, and also in Europe, we are always hesitating a little bit to tackle a problem. Enrique already was mentioning this technological sovereignty we do not establish in Europe, and I would like to hear the opinion also of the bigger companies like Infineon on that.
I think, as you say, regarding sovereignty, is a general development which we unfortunately see. So there's kind of a block formation. You have US, you have Europe, and you have China, and we definitely need the possibilities in Europe to manufacture, especially these important technologies on our own. And regarding Munich, yeah, I think it's a difficult question. It's a kind of a European paradoxon, right? Which we see in many areas. So you have excellent basic research, you have companies, but to transfer this research to real business success is usually a problem for Europeans, which I doubt that we can solve it just like this, also for quantum computing. But what I personally think is that we have to have the guts in the end to think big on money and on facilities. So very often I see that we create something, we create some lab facilities, but they are still in a smaller context. Whereas both in China and US, you see that they generate a lot of venture capital or state-funded capital and really think big and create bigger facilities where you then have an ecosystem combining many, many different players. And this, I think, is lacking.
I think maybe one aspect related to that is also that, I mean, there are kind of many, let's say, opportunities in, not just in Munich, but in Germany for funding startups and kind of startup initiatives. But what's kind of missing a little bit is the level above that, where, you know, real venture capitalist funding can come in and take those kind of ideas to the level where it engages to industry. There's kind of industry at the top, like you said, and the university labs at the bottom, and maybe it's at the level of venture capitalists that we need to kind of think that investment or efforts need to be. It's one thing we don't have as a, let's say, as a culture as much in Europe than they have in the US, for example.
Yeah, and also we have to beyond the claim, right? Because this is a claim, a wish, and everybody agrees. But we have also to make a balance of what is the know-how that we have and that we have developed in the last 10, 20 years, and whether we are really boosting such know-how towards entrepreneurial activities. And I would say, because I'm working here for more than 20 years, for example, trapped ion technologies, they are top groups, we have developed many things, but spinning out quantum computers with trapped ions for sensing, for quantum computers, for quantum simulators is not corresponding to the know-how. If I go to superconducting circuits, that is also a strong know-how. We are not spinning out, and it is a combination, of course, of, as John said, of support, but I think, I mean, I enter here in the category of old people. I think that the younger generations are also reluctant to make the jump. Because I am sure that if some younger postdocs or PhDs decided to go for it, I'm sure they will find resources. I think it's a combination of, it's not only to say it's missing money, investment. I think this American style of, you see, of saying, I open my garage, and this metaphorical way of making the Silicon Valley, right, is missing, and also should be boosted and educated. Of course, if funding is by side, much better. And in China, just to compare, I observe exactly the other extreme. There is too much money, too much funding, and very few ideas and original initiatives. So there is still the philosophy, because they have a lot of admiration for the West. So there is impossible still to break the rule that imitating the Occident is just nice. But to say we create novel things is not yet, and I try to educate the people there also, it's very, very hard. For them is, so let's say admiration goes hand in hand with preserving what has been done and not breaking the pot, right? So in China there is too much funding. What is missing is promoting originality. And I think in Europe there is a balance of know-how and funding. What is missing is the spirit of risking and creating startups, and that's what I see.
Perhaps also a question to you, being professors. So what I also see in the US that very often professors kind of combine their research with their company. You look at John Martinez, who switched over to Google. So what is preventing you of spinning out the company?
Oh,
just waiting for the right offer.
Okay.
I see.
So John, we are waiting since decades for an offer of Infineon
You're talking
to join the company. No, actually, this is an issue in Europe. We are not so flexible, and of course we have a nice system. When you are a professor at a university, you have a very nice job. You are very independent. And this is probably a difference to US. We are not forced too much to do something in this direction. This is probably also what Enrique was addressing regarding young people. And of course, one purpose of this meeting also was that companies can offer and can tell young people what is going on in this field, and you have to tell them that this is very interesting and that they should join the field. And of course, we are telling this to young people in our lectures, but they also should hear that from companies. And at the end, we need this ecosystem to push people to start companies. Yes, that's what we urgently need.
I think related to that, and also to the point that Enrique made earlier on, is actually that you know, we have now, as part of MCQST, this master program in quantum science and technology. So in principle, you have then, let's say, a discipline which is quantum science and technology. And I think maybe it's this generation of people who grow up in that environment that might take that step and become more innovative and be willing to kind of try to take, you know, the next step. Because, you know, if you look at, you can do a master's in electrical engineering or something like that, where, you know, there's a clear industrial and career track waiting for you. And I think in quantum science technologies are kind of turning the other way around. There is a career track there for you, and there is a developing field, but the people with that profile, only that profile, are not yet there. Maybe that's also one thing which might be a game changer.
Good point. Education is crucial. Huh? It's a very good point, John. I observe it. I used to...
your microphone is off.
Oh, sorry. Now, is it better?
I hear you.
Yes. So what I'm saying is, I used to go to give lectures.
Enrique, your microphone.
Hello.
Your microphone.
I hear him.
We don't hear you, or at least I don't hear you. Okay.
Everybody, wait. So let's say I used to go to schools, you see, even elementary schools, high schools, every year to speak about quantum computing. And I am very impressed how the younger generations take this fresh and are very interested, and they absorb very fast the concept. You see,
Okay, now I lost him as well.
I'm afraid it's very likely his connection, because everyone else seems to be okay. Yeah, there we are.
Okay, no, I was just saying that the younger generations are absorbing very fast these concepts. I think at the level of MCQST, it is needed also the last step, right? That we can tell them it's not enough. I mean, at least this is the way I provoke my students, right? I always tell them the worst class of students is the one that sits and applauds how brilliant is a professor, right? In MCQST, there should be a part of the education that is to push them towards the huge business, right? Because the know-how is there. You see, I don't know what is your experience, but all younger students that come to me in the last years, they already arrive having programmed quantum computers. All of them. There is nobody. Everybody played with Qiskit, with this, with that. Everybody knows about quantum computing. So the step towards the entrepreneurial activity is very close. We just have to create, as John said in the master program, PhD program, this message that to create companies is not something so terrible.
Maybe it's a good point to actually take one of the questions from the portal, so it's related to what you just said. So one of the audience members has asked, a little bit general maybe, but what's the main general knowledge and programming language one has to have to start working in the field of quantum computing?
Nothing. I mean, this is the feeling I have, you know. I tell you, in Bilbao, we organized a quantum computing hackathon with the support of IBM. And I can tell you that some of the teams that won, half of the team never studied quantum physics. The other half learned, they came with the knowledge of financial models, the other just because they are curious. You know, in 2 nights, they didn't sleep. And suddenly the guys started to speak about quantum algorithms. So sometimes we are overlooking this potential in the younger generations. That's my message. So it's not, of course, I mean, we are professors, right? So we know that how deep is that knowledge, perhaps not that much. But what I mean is that the people start already by playing with quantum computers before studying quantum physics. And I think we should not underestimate that motivation.
Yeah, well, and if I can add something in terms of programming models, I see that in quantum, the field is much more open than in HPC, where there are a few paradigms which are already consolidated since decades, and different solutions are sort of exotic. In quantum, there are very different solutions. It's unclear what is going to be more convenient at the moment. So there is really room for everyone with new ideas. And this is a really exciting phase, I think.
Okay. Do we have questions from the audience, or?
There is one in the portal at the moment, so it's more to the companies, and that is what do you look for in people who start in your companies?
Mm-hmm.
Obviously, a qualification from one of the top universities in Germany is clear, but I mean,
especially somebody from the group of John Finley and Rudolf Gross.
that was also a general question we had. Does industry miss adequate workforce in quantum science and technologies? This is going into the same direction. So what do you have a lack of people, and this is also important for academia to know whether we are educating the right people and whether they have the right knowledge to immediately support you.
Yeah, at least for Infineon, for the projects that we do on quantum technologies, we also always look for students or PhD students or even somebody to start. So currently it's not easy to find qualified people actually. So I think it's very valuable that there are new master programs on this field, especially as I think it profits a lot, or there's a lot of benefit if you can combine different fields of science and education in order to promote this. Of course, it's hard to say how the situation will be in 2, 3, or 5 years, how the whole field will evolve. So it's always difficult to say if you start now, for sure in 5 years you will get a job. But for the moment, of course, I think it's a very, very interesting field with a lot of prospects for the future.
So we have a question in the portal. Maybe Enrique and Rudolf should cover their ears, but how should Bavaria engage with other quantum computing technologies besides superconducting qubits?
Wow. That's fantastic.
Things like photonic implementations, measurement-based quantum technologies, things like this.
Yes, because my career is long, but I did my PhD in trapped ions, and in fact, when I was visiting IonQ, the company of Chris Monroe in Maryland, he was introducing me to their employees, saying, "This guy is the guy that created the 2-qubit gate that we are still using in the company." And I was very proud because I didn't know that. But and it was in my PhD thesis. So trapped ions, I would say superconducting circuits, cavity QED setups, quantum dots are quite similar conceptually. They have, of course, I understand very well the differences, but I don't think that there is a dominant platform. And my suggestion for collaborating would be, or for suggesting, for promoting efforts, common efforts, is not to force the hardware to do things that is not natural done for. You see, so sometimes people want to do the same thing that succeeds in ions, you want it in circuits, you want it in photons. I think that photons have their own advantages, be for the continuous wave, be for the single photons. Superconducting microwave photons, as you probably know, in the 5 to 10 gigahertz, is very hard to find photon number resolving detectors. So you see, each platform has its advantages and disadvantages. And I would suggest that for the collaboration, we should stop trying to do everything like the other one. On the opposite is to maximize the capacities of each platform. And I think nobody thinks that quantum communication will be done throwing and flying superconducting qubits, right? So this is done with photons. But why not with microwave photons and this kind of thing? So I have the feeling that the platforms can approach, but to force hybrid approaches is not something that should be taken so easy. John Martinez once quoted, probably it's not from him, but I like it a lot. He said, when people do hybrid things, they say that they bring the best from each platform, right? And he said, I only see that they bring the worst. and this is the kind of game. So the idea is not to make a hybrid. The idea is really that the hybrid improves, right? And this, if you have this approach to respect the platform, I think that the communication will be much nicer. Not just to do the same in all of them. But I like a lot this concept. So.
And I also share that viewpoint that maybe instead of hybrid, maybe interfacing is the way we should look at it, and you know, not hybrid for the sake of it.
Exactly.
I also think regarding technology platforms, we have to be quite open. So at the moment, nobody can predict what kind of technology platform we will have in 20 years. If somebody says, I know about that, that would be great. But of course, now in Munich, we are working on superconducting quantum technology. I would say if Rainer Platt would heading Walter Meissner instead of me and Stefan Philipp, we would do IQM quantum computing here in Munich. This is just by chance. When you are looking back to history of semiconductor technology, you should be aware of that technology was changing a lot. And we will see how it is going on. But what we should do in Germany, we should start at some point in doing something, because if we do not start anything, of course, we will be lost forever. and then in 10 years, we will complain about this fact that we depend on important technologies and have to buy them in US or China. And this is what we should probably avoid at the moment. Yeah. Of course, one question also I have on my list is whether big government programs are helpful. Of course, in Europe, we are often believing in big government programs just to push something top down. And this is, of course, one method to do it, but it's also dangerous in some way. And what is your opinion about that? Would a big government program helpful in the present situation?
Well, I think that for sure, with respect to other regions, the public financing is key in Europe with respect to the US. It's a bit my impression. I think this can be useful as long as all the different components of the whole chain that we have from industrial component, from the basic and applied research, the hardware development, the software, the application. So if all these components at some point can benefit from this financing. I can make the example of one call that we have participated. It was a BMBF call, so the Federal Ministry call for quantum software. And among the features of this call, there was to foster the collaboration between research institutions, so academic research institutions, with companies and startups. So all elements to develop an idea, a plan to advance on quantum software, and the fact that all these elements could go together, I think this is crucial for having this financing not just piped to a single channel that would not be beneficial for the community.
I think a lot of it is related in a way to, let's say, political will, because, you know, we've also seen, you know, with the corona pandemic that Western governments, when necessary, can come up with really remarkable levels of funding, providing that, let's say, people want to move in one direction. Of course, the corona pandemic is a very important thing that absolutely needs addressing, and it needs that level of funding. But it kind of does raise the question that, you know, moonshot type projects, where there really is a coherent will across many governments and many countries, can have a hugely transformative effect. Yeah. I mean, we had a similar discussion regarding the photovoltaics yesterday evening in the Munich Physics Colloquium, that, you know, the kind of money it would require to get photovoltaics on the road would actually be small compared to the money that governments have spent, far smaller than the money governments have spent addressing the corona pandemic. And of course, the future of the human race with regards to climate is a very important thing. And you could argue the same, you could argue along similar lines when it comes to quantum science and technology, based on the transformative effect that quantum technologies will have.
I would like to make a nuance concerning that issue. I have been reflecting a lot on this moonshot concept, right? I think nothing against, because this helps, but we should make a huge difference, you know. Let's say the moonshot literally is to put human beings on the moon, or spaceships, at least controllable spaceships. And when you reach, that's it, right? But I think that there is a misunderstanding concerning quantum computer. I think quantum computers do not need to reach the moon, let's say metaphorically. There are many quantum computers that should reach the moon. It should be a massive attack, right? And that's the way, because I think that the specialization will come naturally. There will be optimized quantum computer for machine learning, for chemistry, for material design, for finance, for logistic networks, for optimization problems. And I don't see, this is my understanding, I don't see a single quantum computer doing everything very well. I think we are not living these times. We should continue working to that.
Yeah, okay. My question also was going in this direction, and let me probably be a little bit more provocative. Of course, when you have big government programs, usually the money is shifted to big players.
Should be.
And this is also a question I have, whether it's reasonable to shift now a huge amount of money to big players that are not very experienced in the field.
Yes, I think there's always a pro and a contra. Of course, a big government program helps a lot to create awareness and also to foster the development. But exactly as you say, so then a lot of politics come into play, and then it can be that it's just the biggest players or the biggest institutes which get the biggest share, which then often is not the best for the field. So this is a danger. And the second topic, I think, which is also a European challenge, is that we have a lot of national programs now. So in the economic stimulus package, €2 billion for Germany, but every nation alone is probably will hardly make it to compete against China and Europe. So we always have to also look at how to combine this across borders. So for example, ion traps. I mean, we're also very strong in ion traps, collaborating with Professor Blatt, but in the current BMBF programs, it's hardly possible. So to overcome this barrier is a challenge. Yeah. And yeah.
There's a question from our audience, which is actually pertaining to, let's say, the directions that the field should go. And the question is there some agency that plans the route, let's say, of what is expected to be going on in the near future, say of 10 years, like in the sort of semiconductor industry where we have the international roadmap? Is it even possible to put together an international roadmap for quantum computers? Or does it make sense? I mean, in some respects, I personally think, of course, there are certain things that you could imagine it would make sense. But the problem with these roadmaps is they tend to be about incremental improvements rather than really disruptive new directions in a way. And I'm not so sure that quantum science and technology is ready for that yet. It might be for me a little bit early. I don't know what the other panelists think about this.
I think it sometimes helps also to manage kind of expectations. So very often you see the expectation that in 1 or 2 years we have the general purpose quantum computer which will solve everything and crack every cryptographic method, which is not it will not be the case. So such an international roadmap can kind of level this also expectations in politics. But of course you're right. It's always a kind of an evolutionary approach, and reality might look totally different than if somebody comes up with a great idea. But still, I think it can help to kind of, yeah, especially on that. So to manage the hype, which we currently actually have, and perhaps come there to a more productive and approach.
Yeah, John, I think when we have a joint effort within Germany or even within Europe, we have to develop some kind of a roadmap. But of course, this roadmap should be quite flexible, and we shouldn't push too much and put the expectations to a very high level, because this is very dangerous. Mm-hmm. If we would promise something to have in 3 years and then nothing is working out, then the field would suffer a lot.
That's right. It
has happened a lot in history, and we have to be very careful. My example is always high TC superconductivity, because I was working in this field also for a while. And there were so many expectations, and then the government was also putting so much money into the field, and then most of the things didn't turn out, and then the field was dead, so to say. And this should not happen with quantum technologies, and therefore we have to be a little bit careful. But of course, we should look optimistic into the future, and we should take some risk. Without taking some risk, we will not gain anything. And this is always a subtle thing you have to do.
We have another question from a member of our audience, and that is, what can Bavaria do to grow its quantum industry ecosystem? For example, to encourage more quantum computing companies to emerge or establish local operations?
I am convinced that hardware is crucial, and I would like to see more hardware developers. It is true that also we are missing software developers, no, like quantum algorithms. But my conclusion is that there is a lot already development in algorithms, and we need to see how to map those problems in architectures. ions, in photons, and to grow in that way. But what I think that you saw in one of my slides is that that I see that we are, as a community, overlooking is the influence of quantum computing on the education of schools, you see, elementary schools, high schools, quantum computers hardware accessible for research at the undergraduate level, you see, where the students can manipulate remotely such devices. So I think we have to create ecosystem. For me, it's not only company selling, somebody buying, and somebody providing the use cases and so on. We need really the whole society engaged into that. One of my dreams is to place one quantum computer in a museum, Deutsches Museum, right? So I think that we are missing the dissemination, the outreach, the recreational aspects, mobile apps, education in the schools, and so on. All this, in my vision, is my honest opinion is that the business there, if you want to see it in that way, is much, much higher than the business in big applications. I think that we are overlooking that. It's more or less like saying where you get more money, selling supercomputing centers or selling small tablets for children, right? So I don't know the answer, but I think ecosystem is also the society, it's also the schools, it's also the general public. That's the way I see it.
Yeah, but perhaps also regarding, I fully agree regarding hardware, and there I see that there's still a barrier, as it's kind of a deep tech. So you need a lot of investment, a lot of equipment in order to start this business.
And good internet connection.
Exactly, that would be great. Having a high-speed interconnection in Munich. That would be a good starting point, actually.
Sebastian, can you hear us?
Yes, but...
Oh,
okay. We lost you for a moment.
We lost you for a second.
Yes, it states here that my internet is not stable. So perhaps I try again. So to lower the barrier for deep tech startups. So you need a lot of equipment, a lot of investment, and I think this is lacking, especially here in Munich or in Bavaria. So if you want to do something with semiconductors or fabrication, if I look, for example, for IQM in Finland, at Helsinki, I think it's far easier to access there the facilities than here in Bavaria. And I think there we have to improve in order to make it easier to create a startup.
I fully agree, and you probably know that we are pushing our government exactly into this direction. Of course, this is a big investment. let's say it like that. But it would really make a difference for the Munich area, because I fully agree with you when we have startups in the deep tech regime. They need this high-tech equipment, and they have to rent it, and they cannot buy it and build it up. This would take too much money and too much time, and we have to provide something in this direction. Not only the startups would profit from that, but also the academia and probably even companies like Infineon.
Yes.
This would also just foster collaborations between the different players, because if you have like a center where you can share important infrastructure, that's a meeting point where all different players can meet and build new networks. So similar to what we're now doing at MCQST, I think that's very important. We have a very nice situation here in Munich with so many players and strong universities and strong research, and it's nice to meet here at MCQST. A shared hardware facility which could be used by startups and existing companies and would complement this. I think that would be very important.
I think it's very important as well. I mean, I entirely share these kind of ideas, and I think it's really clear that when you have a construct like MCQST, which brings together into frequent contact industry players together with university groups, it's quite clear that there's so much more that unites us and produces synergetic effects than there is, say, the need to build bridges. It's just need a forum to bring people together, yeah, and the infrastructure to allow that to happen. Yeah.
I completely agree. So having a system on premise in the area would allow to develop the full skill set in operating this, for example, and would allow every user to make a more direct experience with it. And there is also a component that, okay, this goes a bit beyond having the system directly in the Munich area, namely the fact that quantum computing is an area that at some point might become delicate in terms of export control from other countries. So developing a system, I wouldn't say in Germany, but in Europe is crucial if we want to access this technology.
Mm-hmm.
Yeah, I think even our high-level politicians realized that, and just a day ago, Jan sent me a press release of our minister, Karliczek, and she was exactly using these arguments. So this is in principle good news for us, because they see that we have to develop something on our own here in Europe. And of course, we should just raise our hand and say, yes, we can do it here in Munich.
I mean, you only have to look to the kind of situation with the drug that does treat the coronavirus, where the United States recently bought basically the world's supplies of this particular drug. This kind of protectionist kind of activity, of course, will come into force in the current climate worldwide.
Good.
Okay.
Yeah, before we probably close this industry session, I would like to remind you that we have a session on quantum computing coming up in about 25 minutes. We have high-level speakers, so ion trap quantum computing will be represented by Mons from Innsbruck, and we have John Martinez, of course, as a key player in superconducting quantum computing, and so probably we do a short break to eat a little bit and to get new energy for the next session. Okay.
Thank you very much. Also from the organizational side, I would like to, I would like to add something for the audience, because it is actually very nice that all the people who you've just seen, you can also meet in our 2D environment. So, you know, they'll be there. You can access it via the industry poster session on both platforms. You can find them there. You can also, if you're in the 2D environment, enter their name and find where they are, no matter where they are. So you can talk to them. And I would really encourage everyone to make use of this opportunity and, you know, meet people in person, so to say. So thank you again for also staying on. That's really great. And thank you for coming by.
Thanks.
Thank you.
Thanks a lot. Have a good time. Yes.
Bye.
Bye.
Bye.